SwayamPrabha. Digital India. Educated India.
Hello and welcome to the next part of the lecture. So today I'll be talking about how to estimate the drag polar parameters using aircraft data. So we'll learn this experiment today, right? So the objective of the experiment will be this drag polar parameter estimation, and for this experiment we will be using this Cessna aircraft data. So I should write drag polar parameter estimation using Cessna 206H, and we should do this experiment at cruise mode. So at cruise mode, right? So the objective of this experiment is to estimate the drag polar parameters. So from the drag polar equation we know, if you see this equation, drag polar equation, which is CD equals to CD naught plus KC L square. So here you see these two terms, CD naught and K, CD naught and K. So to find CD naught and K will be the objective of this experiment. Yeah. So now it is clear to us, like we want to find CD naught and K from the flight data. So the question arises now, like how will you plan the experiment? Suppose you have aircraft now and you also have a pilot. So how will you conduct this experiment? What should be your plan, and how can you get these two numbers, CD naught and K, right? So I'll just quickly revisit the theory of BHP, which will relate this CD naught and K. So the background is already has been given by Professor Ghosh, so I'll not go in detail. So BHP, as we know, is drag into velocity, right? And you can write further like half rho v square as CD, yeah, into V, and if you further expand, then it will become half rho v cube S, and I'm replacing CD now with CD naught plus KCL square from the drag polar equation, right? So if you break this again, so it will become half rho v cube S CD naught, right, plus, and I want to write CL in terms of velocity, right? So what should I do? So you know CL equals to twice of wing loading divided by rho v square. So CL square is essentially 4 W square by S square rho square v to the power 4. So we have to plug this value here, right? So I'll write half rho v cube S times K, yeah, into 4 W square by S square by rho square v to the power 4. So now you see this will get cancelled here, 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 and then right to here. So further simplification will look like this. So half rho v cube S CD naught plus twice of K W square by, so I should write here S rho times V. So this is actually BHP now. So if you multiply with velocity both the side, So it will look something like this. So can I write like this? Bhp into V equals to half rho V to the power 4, yeah, S CD naught plus twice K W square by S into rho. Now your V will get cancelled because we are multiplying this with V. So this is the equation actually. Yeah, sorry. So now you see CD naught and K both are appearing in this equation, and if you see this relation carefully, then Bhp into V, this is linear with V to the power 4. So if you roughly see the curve, so I'll make it here so that in future we can have the reference. So if I put Bhp into V versus V to the power 4, so it is linear, so it will look like this. So from this curve, if you get to know about intercept, then that will be equivalent to twice of K W square by rho times S, and this slope will be equivalent to half rho S CD naught. Yeah. So now it is very clear, like if we want to get CD naught and K, then we should have the readings for Bhp and velocity, right? So once you plan this experiment, so what we need is following: Bhp and V. Now do we have any instrument which directly can give you the Bhp? So no. So to get Bhp, if you see Bhp, the specification given by manufacturer. So Bhp is basically RPM divided by rated RPM into manifold pressure by rated manifold pressure, sea level temperature, standard temperature divided by outside air temperature OAT into rated HP. Yeah. So if we want to calculate the Bhp, then we need these variables. So from the engine manufacturer, you will get specified values for rated RPM, rated manifold pressure, and rated HP, right? So if you see here, the data provided by manufacturer for Cessna 206 aircraft, rated RPM is 2700, rated manifold pressure is 29.92 inches of Hg, and rated HP is given 300, right, HP. So with those value we can calculate. Now from the flight, can we measure RPM, manifold pressure, outside air temperature, and yeah, can we measure? Yes, we can measure. So we have instruments to measure that. So once you plan your experiment, then you should create a table. In that, of course, you have the instrument to measure the velocity V, and you also have to note down the reading for manifold pressure, right? And next is RPM, right? RPM. And next will be our Bhp. So we can calculate Bhp with the help of these readings and specified data, right? So now you can further create one more column, which will be Bhp into V later actually. So we'll talk about this later. Yeah. So to conduct this experiment, since we have already talked like we have to perform this experiment at cruise mode, then we should also note down what is the altitude, at what altitude we are going to fly the aircraft. So you should know about the altitude. So usually we fly at 300 meter or roughly 1000 feet. So you can write 1000 feet. Like this aircraft is usually fly 1000 feet, and then you can note down the outside the temperature. Yeah. So whatever it is. So just to give the reference, I'll show you one of the experiment done in this aircraft. So one of the group of students actually they have performed, and then they have noted down the velocity like this 103. Yeah, we have to be very careful about the unit. So here in the aircraft you will get velocity in terms of knot, K and OT knot. Yeah. So I'll write here knot. And manifold pressure will come in inches of Hg. So I should write inches of Hg. And RPM is RPM. Yeah. So yes. So if you see here, you will get for 103 manifold pressure was 21.4 and RPM was 2250. Okay. So with that BHP will come around 127582.77. Yeah. Okay. And next column is BHP into V, right? If you see this equation here, I have written BHP into V equals to this. So the velocity which is being used by this equation here, so is it same as what is being read in the dial of aircraft? Is it same? So no, it is not same. So usually in the aircraft you see this velocity reading. This is called indicated airspeed. So indicated airspeed is not a true speed. Here in this equation it is true speed. So you can also write Vt. So this V is nothing but true speed. So now a question arises again, like how will you convert this indicated airspeed to true speed, right? So first of all, for different kind of aircraft you will get the calibration chart. So with the help of that you can convert your indicated airspeed to the equivalent airspeed, right? So if you see, I'll just give you a small now example through this configuration. Suppose for this it is flap up configuration. So here if you got the reading for indicated airspeed in knot, then you can have the corresponding calibrated airspeed. So CAS in knot. So if you have number 60, 70, 80 and so on actually. So I am not writing all the numbers. So just to show you, so for 60 it will become 63 as per the specification, 70 corrected value will be 71 and for 80 it is 79 and for 90 it is 89. Yeah, 89. So now further we need to convert in terms of true speed. So we will use this simple relation actually. So half rho Vt square rho altitude I should write here equals to half rho sea level into V equivalent square. So this is actually V equivalent after the correction. Once you correct your indicated airspeed, so that will become a V equivalent, and from that you can calculate your V true airspeed, which will be square root of SL divided by rho altitude, yeah, times V equivalent. Yeah. So that is how you get true airspeed. So now you can plug in the equation or in your reading. But again, yeah, so we also have to see here it is rho altitude. So it means that we need to correct the density also. So density correction can be done through this relation. So density altitude you can write rho naught. Yeah. So Ts sea level temperature, which you can take 15 degree Celsius, and O80 to the power minus G naught divided by AR plus 1. So here A is lapse rate, you all know. So just I'll write the value. A equals to minus 6.5 Kelvin per kilometer, and R is specific gas constant, so you know about that. So once you corrected your density, so you will get the true speed. From the true speed, we should multiply this. So I should write Vt. So you will get this number now. Yeah. So for each reading, like students, they have performed for different speeds. So just I'll write down the number so that you can appreciate those readings. So 103, 106, and 111, and he has taken their data for 114. So 21.4, 22.1, 22.4, and 22.8, right? And RPM reading was like 21.1, so 22.4 and 22.8, right? And corresponding BHP 1329, 27.20, 134, 731.64, and 11829.689.12. Okay. So now with these readings actually, so these all are the flight data actually during the flying condition. Students, they have noted down those values, right? So now you will have this column BHP into VT, and then you can also have this VT power 4, right? So now coming to this, if you see here, you got this reading here from that table, and then you also have corresponding true speed to the power 4, right? So for this corresponding 4 readings, you will have, you should get linear. So here also it is reasonably linear, right? And with that, the value obtained for CD naught and K are this. So from this slope, you will get CD naught, which is here 0.032, and K came 0.155. So as per these readings, right? Now the number which you got, CD naught and K, how will you know like these are accurate, or what is the confidence interval for those numbers? How will you judge the numbers, right? So what we should do, if you want to validate your K, which is here 0.155, all of us know K can be written like this, K equals 1 by pi aspect ratio and Ostwald efficiency factor E, right? So for Cessna aircraft, if you calculate K, so it will be 1 by pi times, so the value is around 7.448 aspect ratio. You can get the aspect ratio from here, d square by s, wingspan square by this area, and if you take E value as 0.85, yeah, so this number will 0.05 here, you see. Now from the calculation, from the geometrical details of the aircraft, for E being 0.85, you got K 0.05, but you see the number here, it's 0.155. So it means like this is not in the agreement, right? So and CD naught looks to be okay, because the range of CD naught usually will be your roughly 0.02 to 0.04 for this kind of aircraft. So it looks very reasonable. but we did not, or we could not get K value correctly. I will not say like very bad, but yeah, we definitely need some correction on the value. It means we have to look back for to the readings, like maybe because of some instrument error we could not note the reading properly, and it may have certain other human error in that, like which did not go well. But the whole idea is like that. Once you have the aircraft and you want to estimate CD naught and K, so these are the values, or these are the variables we need to note while the flying condition, and with that you will get BHP, brake horsepower, and true airspeed you will convert your indicated airspeed, and you will be able to estimate CD naught and K. So thank you so much.